The region where VDB123 resides is actually very active. Ton of reflection nebulas and also star clusters. Ton of reflection nebula. Alright, hello everyone. So this video is basically about a couple of different stars in Serpens. So this is an extra video. First is SMM1A and 1B. These are binary stars that both have protostar outflows that overlap. 2 is OO Serpens, which is a star that's still forming with a lot of gas and dust around it. OO Serpens has not entered the main sequence part of its life yet, meaning it's not a main star like our sun yet. It had a protostar outburst in 1995, and the brightness output of the outburst along with the surrounding reflection nebula reached its lowest around 2003, and some parts of the reflection nebula have actually gotten a little bit brighter since then. There's been outflow activity for years. Okay, next up we have EC82. So basically, this is a variable star casting a shadow of at least 1.5 trillion miles, which is about 2.5 trillion kilometers. Because the disk is tilted a little bit, that causes a huge shadow. This is that bat shadow I discussed a little bit earlier. However, the disk change cannot be explained by the disk orbiting a star, because the variability is way too fast, meaning that something else close to the star could be changing the disk. Molecular hydrogen outburst 2218 was most likely from EC37, which is another protostar. This protostar outflow is almost pointing directly at us, which looks really cool. 5 is EC53, which is a variable star with its whole variable cycle lasting about 543 days. A variable star changes in brightness, with a binary companion 93 times distance from the Earth to the Sun, which is about 93 AU from us. The companion is most likely a brown dwarf. Issue is that 93 AU is like 3 times Neptune's distance. Keep in mind that Neptune takes about 168 years to orbit the Earth. Variable stars, the only reason they change in brightness is because the binary companion star blocks part of the variable star at some points, changing the brightness. It's like if you put a piece of paper behind a super big light bulb. You'll block some of the light. And the reflection nebula also happens to bright up with the star. But the star's light would spread across the reflection nebula, because that's kind of how reflection nebula works. The light gets scattered. So this means that EC53 must be changing for us to also see EC53 brighten up and down. There must be some other star causing the variability in EC53. We know that the brown dwarf is doing this now. The brown dwarf's gravity is exerting on EC53, causing changes in EC53's mass and physical structure. However, we still haven't found that third star yet. However, hopefully we'll find it soon. Alright, and the last thing in EC53 is that NASA in the JWST telescope had discovered crystalline elements like these, and these crystalline elements are a major discovery. Scientists have wondered for a while why comets get their crystalline elements from, and now we know what it is. This gives us some insight. The star's heat is forming these crystals. Alright, here are the sources, and here are the images once again that I captured. So yeah, bye-bye guys.